Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 1 of 3 on the topic of precipitation frequency analysis and will discuss regionalization variants that go beyond the index flood method. Let's get started. The goal of this and the following lectures on precipitation frequency analysis is to better help you understand the inner workings and assumptions made in studies that rely on precipitation frequency analysis, including products such as NOAA's Atlas 14. Previously, we identified some of the key differences between regionalization of streamflow frequency estimates and precipitation frequency estimates. The lists we see here expand on some of the differences and offer insight into why we have to do different things for precipitation frequency. Streamflow at a gauge is the aggregation of the hydrometeorology of the entire watershed above it. To contrast this, a precipitation gauge measures a small area of the landscape that is essentially one point. Streamflow records have what we would call a longer memory than precipitation. The flow of a river at any given time is strongly related to the flow that happened in the recent past and the flow that will happen in the near future. For precipitation, the process is much more chaotic and storm events may be very brief, with periods of dry punctuating storm events. In the United States, streamflow measurements are primarily provided by the USGS and form a single point of service for obtaining them. While the NCEI catalogs several precipitation observation data sets, they are not uniform in nature. The NCEI catalog is also not exhaustive, and sources of precipitation data are available from a wide range of providers. Partly this arises because it is much easier to measure precipitation than streamflow. Another upside to the USGS being a central clearinghouse for streamflow data is that it's meticulously quality controlled prior to being published. Quality control for precipitation is much more variable, and errors can be introduced in the precipitation observation process in a number of ways. Finally, historical and paleoflood information can be used in streamflow frequency analysis in a meaningful way. Bulletin 17C and the expected moments algorithm was developed in part to use these data to their fullest. Unfortunately, there's not a similar way to use paleoflood or historical precipitation information in a precipitation frequency analysis. The three biggest differences between streamflow and precipitation frequency analysis boil down to these three items. First, in precipitation frequency, it's hard to use paleoflood or historical flood information in the analysis. These can have a tremendous benefit to flood frequency analysis, so we are definitely missing out on them when we're doing precipitation frequency. On the other hand, regionalization has much more benefit to precipitation frequency analysis, and fortunately, it's easier to perform. This helps overcome some of that deficit we have due to missing out on historical flood information. Finally, due to differences in data, quality control becomes a significant task in a precipitation frequency study. Often, it's the majority of the study time and effort. Errors in the data can have a disproportionate effect on the results, and we'll see why during our quality control discussion. Mel Schaefer is a pioneer of precipitation frequency analysis for dam safety studies. I've been fortunate to collaborate with him on work in the past, and he's full of insight about the precipitation frequency process. He said to me once that Mother Nature may have steep gradients, but she doesn't have discontinuities. What he meant is that we have to be careful when we apply our regional frequency analysis results, because the results applied piecemeal can result in discontinuities in space. We saw the index flood regionalization approach in a previous discussion, but it does have a significant drawback in that it calls for discrete regions to be carved out of our study area. These can result in noticeable discontinuities in our results when we go to draw maps of them. From the previous discussion, we recall how the index flood method works. We find a regional frequency curve called the regional growth curve, and it tells us how much the index flood for the sites in the region gets larger depending on the frequency of the event. Then, to make estimates at any site, you multiply that regional growth curve by the site's index flood, which is typically the mean annual maximum event. The limitation is that every place you want to make an estimate has to be placed inside a specific region. Usually, these are non-overlapping geographic boundaries. One frequently used example is the National Weather Service climate regions. If the regional frequency curve for two adjacent regions has a very different shape, the geographic boundary can cause a sharp and abrupt change in the precipitation maps. This can be caused by a large difference in the regional L moments, or also if you choose a different probability distribution for your regions. Early volumes of Atlas 14 had this issue. In some locations, this was solved by using a smoothing algorithm after the fact to fix these abrupt changes, but in some volumes, the sharp boundaries can still be apparent. Here is an example of a discontinuous boundary out of Atlas 14 Volume 1. This is for the 24-hour duration at 1 in 1000 ACE. You can see how the state line between California and Nevada forms a sharp boundary in the estimates for precipitation depth. Artifacts like this are generally caused by some kind of discontinuous regionalization. Changing probability distributions across regions amplifies the problem, especially at small ACE values. The choice of model matters the most at the tails, so checking 1 in 1000 rainfall might turn up interesting results. This is a table from the back of Volume 1, where we can see the process that was used for determining which probability distribution each region would use. We see that across these regions, they vary between the generalized logistic distribution, generalized extreme value distribution, and the generalized normal distribution. If regions with very different distributions, for example, generalized logistic and generalized normal, if they were adjacent, they could diverge a lot. The L moments for these adjacent regions are likely to be somewhat similar, but as the ACE gets smaller, the model controls the shape of the extrapolation more and more. We would like to avoid regionalization artifacts like these sharp boundaries. Making pretty maps is somewhat tongue-in-cheek, but maps that are spatially consistent tend to be visually appealing. Discontinuities look and feel wrong when we see them on a map of something that's natural, so we tend to want to make them look pretty. I mentioned that Atlas 14 has used a spatial smoothing technique to avoid these kinds of discontinuities. This is certainly an option for making the map spatially consistent. Atlas 14 also uses smoothing across durations to ensure that shorter duration storms never have more depth than longer duration storms at the same frequency. One key effect is that in looking at the results, at any point it is almost impossible to estimate the point frequency distribution even when you know the quantiles and the probability distribution. This comes up when people try to use the results at a point, presented as an IDF table, and back out what the distribution parameters would be for that point so that they can extrapolate beyond the 1 in 1000 ACE event. I wouldn't recommend trying to do that. Eventually, as further volumes of Atlas 14 were developed, the process was refined and more sophisticated regionalization techniques that address some of these problems were used. We will talk about a few of these methods next. This table is from Hosking and Wallace 1997 and has more details about several different regionalization methods. At site is where we started. You do an analysis for the site that you're interested in and use the parameter estimates you get for the period of record there. Regional shape estimation is a step in the direction of regionalization by doing a regional analysis and regionalizing, and then pushing down a regionally estimated shape parameter to the site predictions. Index flood is what we've talked about so far. Hierarchical regions gives more refinement but does not solve the discontinuity problem. Within a large region, there are a number of subregions. The large regions are intended to capture variability in shape parameters, while subregions capture variability in dispersion parameters. We will talk about fractional membership next, but this is the first one that addresses some of the spatial discontinuity. It's like index flood with an additional step. Region of influence is extremely different than the others and has been used in Atlas 14, so it's worth understanding. Mapping is an excellent way to produce spatially coherent maps, and it's my preferred method, which is something that I got from working with Mel Schaefer. Bulletin 17 is shown for comparison's sake. You can see that it's similar to regional shape estimation, except instead of replacing the at-site shape parameter, it uses a weighted average of a regional shape parameter and the one at the site. Fractional membership is an extension of index flood that lets each site's region assignment be a little more fluid. The process starts with the normal index flood regionalization analysis, but instead of using a single regional growth curve to make predictions, you use a weighted average of all the region's growth curves based on how similar the site is to each region. Usually, the similarity is measured by things like how close the site is to a region, or its similarity in climatic properties like precipitation and temperature. You might use its elevation and other things like that. This means that the regions in the analysis that the site shares physical properties with have more weight in estimating that site's precipitation frequency curve. This can also be used to fill in the gaps between stations and draw a continuous map fairly easily. It requires a spatial estimate of the index flood and then a way to measure the site's characteristics that's spatially continuous. We'll show an example next. Imagine a scenario where there are two primary factors in determining the regions, and they're the elevation of the site and the average annual precipitation. You found that there are three regions in your study area, and they vary by elevation and precipitation. Region A has the lowest elevation and precipitation, and Region C has the highest of each. If you want to make an estimate for a site's frequency curve, you want to take a region average of all three regions in the study, with the weight of each region being proportional to how well the site belongs to each region. Note that this site doesn't have to be an actual precipitation gauge. It can be anywhere we can estimate the elevation and average annual precipitation. The graph on the lower left is a plot of the two primary regionalization variables, elevation and mean annual precipitation. The three regions are plotted on the graph as red circles. The site of interest is shown as a black dot. The distance between the site of interest and each region is measured as a standardized Euclidean distance. The distance is standardized because the two regionalization variables have different scales, and we don't want one to have more weight simply because its values are larger. These distances were normalized using range normalization. In the table on the right, we see the standardized distance for each region. The weights are computed so that small distances result in larger weights. In this case, the reciprocal standard distance was used. You could see how you could do this for any location in your study area. You could see how a site that is in between the regions will smoothly interpolate between those regions. However, when sites start to get really far away from the regions, you could see how problems might arise. Region of influence does not start the same way as index flood does. ROI fundamentally changes how regions are created and uses the mantra, every site is a region. This works by iterating over every site in the study area, finding some number of sites that are similar to the site using similar criteria we saw in fractional membership, and then creating a region out of those sites, and finally estimating the regional growth curve. The number of sites in each region might vary from site to site. Typically, there is some target number that it aims to gather together, but in situations where a site doesn't have a lot of other sites that are similar, some criteria that cuts off the maximum dissimilarity metric might reduce the total number of sites in the region. On the other hand, in areas where sites are very dense, more sites in a region may be allowed. Here's a simple example using a small subset of sites in western Washington state. The site we want to make the estimate for is shown inside the red circle of the map on the left. We've chosen a target of 3 other sites to include in our region, and we're solely basing our similarity based on physical proximity. In real life, you'd probably choose a value of k much greater than 3, with a typical value closer to 20. The table in the top center shows the site where the prediction is being made in the first row, and then the 3 nearest sites in the rows below it. For each site, we're concerned with the first 4 L moments, which will be used to compute the regional probability distribution parameters. The row at the bottom of the table in red is the weighted average of each of these 4 sites, with the weight determined by the record length, which is shown in the very first column. We treat the weighted average L moments as the regional L moments, and then compute the parameters of the regional kappa distribution from them. The resulted fitted regional probability distribution is shown on the graph on the bottom. Just because the sites are close doesn't completely explain why they're similar. If there's a station in a valley at the foot of a steep mountain, and then a station on the mountain, they may be mutually the nearest stations. However, they may have extremely different observations at those locations, and this should be taken into consideration. Physical proximity is a good start, but if there are better variables for quantifying the variation in rainfall, then use those instead. It's best to choose classifiers that are spatially continuous so that you can make estimates anywhere. The red circle on the map on the right does not have a site in it, but if elevation is the most important consideration for our regions, I can form a region for that location by grabbing all of the sites nearby with similar elevations and taking an average of their L moments. When computing the regional average L moment ratios, you might not only weight the values by record length as we saw in the example, but also by similarity to the site that you're making an estimate for. Weighting by record length takes into account the increase in uncertainty about the L moments for a location due to sample error. Weighting by similarity gives more similar locations more weight in estimating the regional probability distribution than less similar sites. Finally, we reach mapping. Mapping allows you to provide estimates for L moments or the frequency distribution any place you can make a reliable prediction. It also allows you to avoid assigning a site or location to a single region, similar to fractional membership. There are two general approaches to mapping. One is to do interpolation, where you estimate the L moments for all of the sites and then use an interpolation scheme to fill in between them. Then, with the maps for each L moment, you can estimate the parameters of the frequency distribution anywhere you have mapped the L moments, and then the frequency rainfall. The other option is to use spatial regression, which predicts the L moment ratios using a regression model based on spatially distributed parameters. This is the method that I use the most frequently. To do interpolation, you start by estimating the L moment ratios for all of the sites. Next, you choose an interpolation model. Some interpolation schemes typically in play are inverse distance weighting or kriging. IDW can be used with a bias grid to imprint some kind of meaningful spatial pattern on the interpolation result, for example, elevation. IDW has the nasty property of producing a bullseye effect around local maxima and minima, which are not based in reality. Kriging is much tougher to implement but has a lot of advantages, including the ability to quantify uncertainty in the interpolation scheme. Spatial splines could also be used. Finally, once you have the interpolation model, you produce an interpolated map of the L moment ratios so you can estimate them anywhere in the study area. There are two limitations to interpolation. The first is that there's no physical explanation for the variation that you see in the maps. The landscape could have rapidly changing elevation or other physical features that the interpolation can't see. This can be very limiting in rugged terrain or in places where the gradient of precipitation changes quickly. The second limitation is that, especially when using methods like inverse distance weighting, that the interpolated result is dominated by the nearest observation. This severely limits the benefit gained by using regionalization because the estimates are going to be very close to each single site. Spatial regression builds prediction models for the L moments that try to explain why an L moment varies in space. We will see regression in more detail later, but we've already seen enough introduction to the topic that this should still be easy to follow. The predictors in the model are spatially based so that we can apply the fitted model anywhere that we can estimate those predictor variables. This makes data such as elevation and mean annual precipitation attractive because they're available continuously throughout the domain. An example of this type of model is for L mean. Here, we predict this as an exponential model where log L mean is a linear function of the mean annual precipitation. This model is fitted to all the sites in a study, so the regionalization model for L mean may contain hundreds or thousands of observations. When the model goodness of fit is high, these regression models can be very powerful and based on a large amount of information. One word of caution is that although prism-based predictors are spatially continuous, they are modeled products and contain their own assumptions and errors. However, Prism is generally a very good data set to use in these types of regressions. You are going to perform a mapping type regression for L mean in the simple linear regression workshop for this class, and one for LCV for the multiple linear regression workshop. So you'll have an opportunity to explore some predictors that help explain how these L moment ratios vary in space. For L1, you can build a model with any number of predictors, but I doubt it's going to get much better than a precipitation-based predictor like annual or seasonal total precipitation available from Prism. Across several studies I've performed, the L mean can consistently be predicted with a seasonal or annual precipitation predictor very well. For LCV, there's substantially more sample error in these estimators, and depending on the behavior of sites in your region, you may elect to use anything from a site-level regression to a regression that uses groupings of small subregions up to region-level averages. In less dynamic terrain, site-based regression may be possible. In highly dynamic areas, some amount of averaging may be necessary to uncover trends. Subregions are occasionally used in these studies. Sometimes the study will rigidly use the Weather Service climate regions as the regional boundaries, which may or may not be homogeneous regions. Then, the regions are subdivided into smaller homogeneous subgroupings, maybe 2 to 5 per region, to create homogeneity in each subregion. Then, you could capture the variability within regions for the parameter that you want. For L skew and L kurtosis, the sample error is substantial, and estimating these generally require regressing region averages, or in the case of L kurtosis, using a study area average value as the regional L moment. Region average predictors are computed as the weighted averages of all sites in the region, with the weight taken from the site's record length. This gives the sites with longer record lengths a bigger weight in computing the region average. Then, once the region averaged L-moment ratios are computed, use these in the regression model. The predictors for a region should be an average of its properties. The reason we can take a region average and use it in the regression is because a region is assumed to be a homogeneous sample of rainfall. The sites in a region are assumed to be a random sampling of the same precipitation process, with only small variations caused by small, smooth, systematic changes in climatology and sample error. When we take the region average, it represents the parameters we would expect to see of all the sites in the region if we had a large enough sample. Usually, the L-mean is allowed to freely vary to capture those smooth, systematic changes in climatology, with the average of the higher L moments being the true value of all of the sites in the region that they would eventually have with a large enough sample. When using region-level predictors for those higher L moments, we are stating that those regions are homogeneous samples. This means that we reduce the number of observations from hundreds to potentially thousands of varyingly homogeneous stations down to a handful of regions that each represent a homogeneous grouping of rainfall extremes. The downside to this is that the sample size gets much smaller. Be careful not to over-extrapolate. This regression shows predicting LCV using region average predictors. This study used seasonal total precipitation and seasonal average temperature to explain the variability in region average LCV. Notice that there are only a small number of regions, so these models have to be very careful and not overfitting the data. Here is the result of using IDW interpolation and region-level spatial regression for LCV. On the left, LCV was computed for each site and then interpolated using IDW. On the right, a regression model was built for LCV based on physical properties of the sites. The difference shows that the site in the middle of the pink bullseye might be an outlier and has completely wrecked the interpolation. In this area, the elevation and total annual precipitation increases very quickly. Total annual precipitation and LCV of maximum precipitation usually have an inverse relationship, and the interpolation fails to capture the physical behavior occurring in this area. The spatial regression result makes the assumption that the regions are homogeneous and so their physical characteristics and L-moment ratios are very related. This means that we can identify small-scale features, such as rapid changes in elevation, as long as our regression model identifies them. In this situation, the model captures the intensification of rainfall at high elevations, resulting in the dark green patch in the middle, and then the variability induced by the rain shadow to the northeast of the mountains. In order to create precipitation frequency maps, also called isopluvials, the stack of mapped L-moment ratios are used to estimate the precipitation maximum probability distribution for each grid cell in the raster maps. Then, for each of those grid cells, the rainfall associated with a given frequency, for example 1 in 100 AEP, can be computed from the probability distribution. When this is estimated for each grid cell, and the depth for each grid cell for a given frequency are shown, the result is the map on the right, which is an isopluvial map. In this video, we discussed regionalization variants beyond the index flood regionalization method. Thanks for sticking with me through the whole thing. Two key points to take away from this video are: more sophisticated regionalization techniques that build on the index flood concept can help produce spatially coherent frequency maps, and if we apply rigid regions in our study area, we may create mapping artifacts that require us to smooth the result before we're finished. Thanks, and tune into the next video in this series on precipitation frequency analysis to learn about data quality control for precipitation frequency studies.